Okay, these are the answers to the packet on Chapter 10, which has to do with gases. Section 10.1, Characteristics of Gases. Part A, name 3 characteristic properties of gases mentioned in this section. And you will find these mentioned on page 384. Expanding to fill a container is one property. Being highly compressible is another property. And forming homogeneous mixtures is another property. These properties of gases can be explained by the fact that gas particles are relatively far apart from each other. Section 10.2 is on pressure. The definition of pressure, as given by equation 10.1, which you can see is pressure equals force divided by area. And we define as the force exerted by the atmosphere on a given surface area. That's the definition of atmospheric pressure. In the 17th century, many scientists and philosophers believed that the atmosphere had no weight. Evangelista Torricelli was able to prove that air does in fact have weight. He invented the barometer, which is illustrated in figure 10.2. Although there are a wide variety of units that can be used for pressure, the AP Chemistry exam uses 3 units for pressure: atmospheres, millimeters of mercury, and torr. And those 2 units are equivalent. There are 760 millimeters of mercury, or 760 torr, in 1 atmosphere. The diagram on the right shows an open-end mercury manometer. So we have a sealed container on the left that is going to have a particular amount of gas in it. And on the right, we have an open tube that's open to the atmosphere. Suppose the atmospheric pressure in the laboratory is equal to 764.7 torr. The gas pressure in the sealed flask would be higher than 764.7 torr, and we know this because the mercury level on the side closest to the sealed flask is lower than the mercury level on the other side, which is open to the atmosphere. That means that the gas in the flask is pushing harder than the atmosphere is. Now the difference between the 2 sides is equal to 32.6 millimeters. So therefore the pressure of the gas would be 32.6 torr higher than the atmosphere. So the pressure of the gas in the sealed flask is 797.3 torr. And now that we know that, to convert that into atmospheres just requires us to take 797.3 and divide by 760. So the pressure in atmospheres would be 1.049. If you were to transport this open-end manometer to the top of a mountain, the value of h, which is the difference in height between the 2 sides, would increase. And the reason why is because the pressure on the higher altitude would be less than it is at sea level. So therefore there would be a greater difference in pressure between 797.3 torr and, for example, maybe 750 or 745 torr at a high mountain. It mentions that Pascal took one of Torricelli's barometers up to a mountaintop and discovered that there was less pressure pushing down on the mercury in the dish. So this was able to prove that the idea that the atmosphere does have weight. All right, section 10.3, the gas laws. Robert Boyle discovered that when the pressure on a fixed sample of gas is doubled, the gas volume is, well, let's take a look at a diagram. Here we have an atmospheric pressure of 760 torr, and we have a gas volume of 60 milliliters. They added an additional amount of mercury, and the volume decreased to half the original value. We doubled the pressure, so it was 760, but now with the extra mercury and the atmosphere added together, the total pressure on that particular sample of gas is doubled, so 1520. So you can see that the answer in the first blank for gas laws is decreased to half its original value. Boyle's law is an inverse relationship between pressure and volume. So when the pressure is 2 atmospheres on this graph, the volume is 50 milliliters. When the pressure is doubled to 4 atmospheres, the volume is cut in half to 25 milliliters. And if the pressure were 10 atmospheres, we expect the volume would be 10 milliliters. What we're doing is pressure times volume. So 2 times 50 is 100, 4 times 25 is 100, so 10 times 10 is 100. Now for the other point, we're doing what number times 15 equals 100. And if you do that math, you get 100 divided by 15 is 6.7. So as you can see, there is an inverse relationship between pressure and volume, and that's why the graph looks like that curve. Okay, so we've looked at Boyle's law. The next gas law we're going to talk about is Charles' law. Jacques Charles discovered the fact that when the volume of a fixed sample of gas at constant pressure is going to be affected by an increase in the temperature, this is not an inverse relationship, this is a direct relationship. So the volume will increase as the temperature is increased. You can see the straight line on this graph, and if you extrapolate that line to the x-axis, at what Celsius temperature would an ideal gas have a theoretical volume of 0? That would be at absolute 0, which is approximately negative 273 degrees Celsius, which is kind of what it looks like on the graph. The official definition of absolute 0 is negative 273.15 degrees Celsius. So we'll go ahead and typically use negative 273 as our estimate of absolute 0. What does that mean? It means that when you're going from Celsius to Kelvin, you add 273. So here we have an example of a Charles' law problem. We're heating a gas and the volume should increase. Does the volume increase? Yes. Does the volume increase from 1 liter to 3 liters? No. And the reason why you disagree with this statement is because we're not looking at the change in Celsius temperature. We should be looking at the change in Kelvin temperature. So yes, the volume does increase, but when you do the math, it's going to be by a factor of 348 Kelvin divided by 298 Kelvin, and we get that the new volume of hydrogen is 1.17 liters. So always convert temperature from Celsius to Kelvin when doing gas law calculations, and you just add 273 to the Celsius temperature. Another gas law relationship has to do with the law of combining volumes, and this relates to our knowledge of stoichiometry. So even though 2 liters of hydrogen gas are being combined with 1 liter of oxygen, we're not going to make 3 liters of water vapor. Because we're doing a chemical reaction here, there should be a 2:1:2 mole ratio between these chemicals in the balanced equation. And since mole ratios are the same as volume ratios, assuming constant pressure and temperature, we're going to make 2 liters of water vapor based on the stoichiometry and the mole ratio. Similarly, we have a balanced chemical equation for the formation of 2 moles of ammonia from 1 mole of nitrogen and 3 moles of hydrogen. But I could consider the mole ratios the same as the volume ratios. So 1 plus 3 in this case actually equals 2 according to the mole ratios. Now, Amedeo Avogadro interpreted the law of combining volumes and proposed that equal volumes of gas at the same temperature and pressure should contain the same number of molecules. So that means that not only are volume and moles proportional, but we can assume that if we have the same volume, the same temperature, the same pressure, we contain the same number of moles or the same number of molecules. So in these 2 balloons, that's exactly what's going on. They're at the same pressure, which is 1 atmosphere. They have the same volume, and they have the same temperature of 0 degrees Celsius or 273 Kelvin. The balloon on the left contains 2.016 grams of hydrogen, which is exactly 1 mole of hydrogen. Therefore, we have Avogadro's number of molecules in the balloon on the left. The balloon on the right would also contain 1 mole because it has the same volume, temperature, and pressure, and 1 mole of oxygen gas has a mass of 32 grams. Now the volume of the balloon you'd have to remember from your Chemistry 1 days, because we haven't quite gotten to the ideal gas law yet. And maybe you remember that 1 mole of any gas under standard temperature and pressure, which is 1 atmosphere and 0 degrees Celsius, the volume would be 22.4 liters, and you can prove this once you plug in the information into the ideal gas law. Now each of those gases had the same temperature, therefore they had the same average kinetic energy. But are these molecules traveling at the same average speed? And the answer is no. Now the reason why has to do with the fact that kinetic energy relates to temperature. However, lighter gas particles travel at a faster average speed than heavier gas particles. So the hydrogen molecules, which are lighter, are traveling at a faster average speed than the heavier oxygen molecules. Okay, now we are considering in letters J, K, and L different situations, and we have to decide if certain variables are going to increase, decrease, or remain the same. We can assume that the amount of gas, or the number of moles, is constant. So here we have a sample of gas is heated. So temperature is increasing. Volume is constant. Well, if temperature is increasing, then pressure should also increase because the molecules will be colliding with the walls of the container more often. And they are going to be traveling faster. The density of the gas should remain the same because we have the same mass and we have the same volume. The average distance between the particles should remain the same because the volume is constant and the mass is constant. The average speed should increase because the particles are hotter and therefore traveling at a faster speed because of the increase in kinetic energy. Our next example, we still have a constant number of moles, but now we have a constant temperature. So therefore the variables that are changing are pressure and volume. Because we are decreasing the volume, the pressure should increase. We have the same sample of gas, but now it's confined to a smaller container, or a smaller space. The density should increase because we have the same mass in a smaller volume. The average distance between the particles should decrease because these gas molecules are now confined to a smaller volume. But the average speed should remain the same because the temperature remains constant. In this next example, what is going to be constant is the volume and the temperature. So what's changing are the amount of gas and the pressure. If we pump additional gas into that rigid container, the pressure should increase because we have more collisions with the walls of the container. The density should increase because we have additional mass of gas for the same volume. So we've increased the amount of gas. The average distance between the gas particles should decrease because we have a larger number of molecules confined to the same space. And the average speed should remain the same because the temperature is constant. So moving on now to section 10.4, the ideal gas law equation. We know this from Chemistry 1. The ideal gas law is PV equals nRT. And we see a variety of numbers in our textbook for the ideal gas law constant. The two gas constants that we typically use in AP Chemistry are 0.08206 and 62.36. If we use that first value, then we have to make sure that the pressure is in atmospheres, the volume should be in liters, and the temperature, as we know, needs to be in Kelvin. If we use 62.36, then the only units that will change relative to the information in Part B will be the units for pressure, which become torr, or millimeters of mercury. Let's go ahead and use the ideal gas law to calculate the pressure inside a helium tank that has a volume of 17.8 liters and contains 30 grams of helium at a temperature of 22 degrees Celsius. So what are we doing in this problem? We're going to calculate the pressure from the ideal gas law. So pressure equals nRT over V. Let's figure out the number of moles of helium. We'll take 30 grams of helium, divide by the molar mass of helium, and so we end up with 7.50 moles of helium. Let's convert our temperature from Celsius to Kelvin, and let's plug in the information we need for the ideal gas law. So we'll go ahead and do this calculation, and we get a pressure of 10 atmospheres. The reason why I'm calling it 10 with a decimal at the end is because I want 2 sig figs, and the reason why I want 2 sig figs is because of the temperature. 22 degrees only has 2 sig figs. So another equation which is in this same section is not the ideal gas law, but what's called the combined gas law. This relates pressure, volume, and temperature. So here we have a pressure of 1 atmosphere for this balloon at sea level. We have an initial volume of 30 liters, and the temperature starts out at 25 degrees Celsius or 298 Kelvin. As this balloon rises to a higher altitude, the new pressure is, we don't know. The new volume is 55 liters, and the new temperature is negative 19 degrees Celsius or 254 Kelvin. If we go ahead and solve for the new pressure, we end up with 0.46 atmospheres. And again, that makes sense because at a higher altitude, the atmospheric pressure would be less. All right, moving on to section 10.5, further applications of the ideal gas equation. We know that density is mass over volume. Show how the density equation can be converted into D equals mP over RT, where M stands for the molar mass. Let's go ahead and use the ideal gas law equation. Volume is equal to nRT over P. So we've substituted for volume. We know that molar mass is mass divided by moles. So when we substitute the capital M for molar mass into this equation, we have mass over moles. We get molar mass over the expression RT over P. And that just rearranges to molar mass times pressure over RT. Look at the inverse relationship between density and temperature. So what I mean by that is that as the temperature goes up, the density goes down. Hot gases have a lower density than cold gases. That's going to be coming up in our next example. The density of dry air at STP, so 1 atmosphere and 0 degrees Celsius, is 1.29 grams per liter. What is the density of dry air at 100 degrees Celsius? So if I have 1 liter of dry air at STP, it has a mass of 1.29 grams. If a fixed sample of gas is heated, the volume should increase. That's according to Charles' law. So that 1 liter of dry air at STP is going to have a larger volume at 373 Kelvin, which is what 100 Celsius is. The new volume of gas would be 1.37 liters. So that same sample of dry air, which still has a mass of 1.29 grams, has a density, when you do mass divided by volume, you get density, of 0.94 grams per liter. Just as we predicted, hot gas is less dense than cold gas. So yes, this does seem logical based on hot air balloons because they rise. Hot gases are less dense than the air outside them. The air inside a hot balloon should be less dense than the cold air outside. Okay, so this particular problem is an old AP chemistry example that relates to gas density. So we have all this given information about a particular flask that contained dry air. And our first task is to calculate the mass of the dry air. Now we really can't do anything with 157.70 grams. That's not going to help us because we have no idea what the mass of the empty flask was. But we can do something with 843 milliliters. If we know that the density of the dry air at these particular values of temperature and pressure, if that density is 1.18 grams per liter, we can use that as a conversion factor. So 1.18 grams for every 1,000 milliliters. That helps us convert from volume to mass. Okay, so our answer to part A is 0.995 grams of dry air that was in the sealed flask. Well, now that we know the mass of the air in the flask, and we know that the mass of the sealed flask with the dry air was 157.70, all we have to do is subtract, and the mass of this flask itself is 156.71. Remember that when you're subtracting numbers that have different number of decimal places, you always round off your answer to the fewest number of decimal places. Okay, so on to part C. If we know the mass of this empty flask, we can subtract 158.08, so minus the mass of the flask itself, and that gives us a mass of this mystery unknown gas of 1.37 grams. Interestingly, we know that the unknown gas is more dense than the dry air. That's because the mass is heavier. So whatever this mystery gas is, it's more dense than dry air. Let's calculate the molar mass of this gas. So we're going to use PV equals nRT. We have the pressure, we have the temperature, and we have the volume. So let's calculate the number of moles. So we're going to use 750 torr, volume in liters, so 0.843 liters. There's the gas constant with torr units, and the temperature is 23 Celsius or 296 Kelvin. So that's the number of moles. I'm using some extra digits because I haven't rounded off my final answer yet. Recall from part C that we had 1.37 grams of this unknown gas, and that gives us a molar mass of almost exactly 40, so 40.03 sig figs. Now what do we do with this 40.0? Well, we compare our calculated value of the molar mass with the accepted value, and we get a percent error of around 9.1%. Our calculated value for molar mass was too low. It was too small. We've got two different examples of a situation that could have caused this error. So did this first example cause the mass, the molar mass, to be too low? Some of the dry air remained in the flask. Remember that this carbon dioxide is more dense than the dry air. So yes, this occurrence could have caused the error. Since dry air is less dense than carbon dioxide, if some dry air remained in the flask with the CO2, this would have caused the mass to be too low, and therefore the calculated value for molar mass would be too low. But if the CO2 was actually colder than the reported 23 degrees, cold CO2 would actually be more dense. So no, this could not have caused the error, because a colder sample of CO2 is more dense, and this would have caused the mass of CO2 to actually be too high, and that would not have explained the error in this experiment. All right, so our next part of this question: describe the steps of a laboratory method that the student could use to verify the volume of the rigid flask. Well, one method would be to just find the mass of the empty flask and then fill it to the brim with a liquid of known density, such as water. Measure the mass of the liquid-filled flask, subtract to find the mass of the liquid, and then use mass and density to calculate volume. Another sort of simpler method might just be to simply fill that flask to the brim with water and then carefully transfer that water to a 1,000 milliliter graduated cylinder and record the total volume, which is hopefully going to be 843 milliliters. One application of the ideal gas law is a situation involving stoichiometry calculations where gases are either consumed or formed. Here we have a gas that's being formed from a decomposition reaction. We start with sodium azide, which is NaN3, and it decomposes to give sodium and nitrogen gas. If we balance this equation, the coefficients are 2, 2, and 3. And if we start with 75 grams of sodium azide, we can convert from grams to moles. after we convert from grams to moles, sodium azide is not a gas. It's the nitrogen that actually fills the bag. So we have to convert from moles of sodium azide to moles of nitrogen using the mole ratios, the stoichiometry. Okay, so we have 1.7 moles of nitrogen. We already have the temperature and the pressure. Let's calculate volume. So V equals nRT over P. And the volume in liters works out to be 38. So 38 liters of nitrogen gas in the airbag. All right, on to section 10.6, gas mixtures and partial pressures. Dalton's law of partial pressures states that the total pressure of a mixture of gases is equal to the sum of the pressures that each gas would exert if it were present alone. And on page 400, we have an expression for mole fraction, which is a ratio of the part divided by the whole. So this fraction would be moles of a particular compound divided by total moles. How can we use the partial pressure of a gas in a mixture, which is called P1, and then the total pressure of the gas mixture, P total, to calculate the mole fraction? Well, remember that mole ratios are proportional to pressure ratios. So if we know the partial pressure of one gas and we divide that by the total pressure, that would be the same as the moles divided by total moles. So pressure ratios are proportional to mole ratios. If we have a mixture that contains equal masses of oxygen and helium, let's go ahead and consider just as a random number, well, not really totally random, but as a specific number, 32 grams, we'd have exactly 1 mole of oxygen gas, and we'd have 32 divided by 4, we'd have 8 moles of helium. The total number of moles would be 9. So the mole fraction of oxygen would be 1 over 9. The mole fraction of helium would be 8 over 9. If the total pressure is 2.70 atmospheres, then we know that 1/9 of this is coming from oxygen and 8/9 of this is coming from helium. So our pressure of oxygen would be 0.3 and our pressure of helium would be 2.4. Again, helium's pressure is 8 times larger, which is consistent with the mole ratio. In this question, we have two gases, hydrogen and methane. They are in separate flasks and they are connected by a valve which is currently closed. The flask on the left has a volume of 10 liters and the pressure of the hydrogen is 3 atmospheres. The flask on the right has a volume of 4 liters and the pressure of the methane is 2 atmospheres. Now you might think that all we have to do is add the two pressures together. 3 plus 2 is 5. But we have to do more than that. That would be incorrect. It says calculate the total pressure of the system after the valve is opened. The pressure of the hydrogen is not going to remain at 3 atmospheres. When that hydrogen expands to fill both sides of this container, the final volume of hydrogen gas is going to be 14 liters. And then the same thing happens to the methane. The final pressure of methane will be less than 2 atmospheres as it expands. So we're going to solve this problem using Boyle's law. And we have to do it twice. We have to do Boyle's law for the hydrogen and do Boyle's law for the methane, and then add those two pressures together. So for the hydrogen, P times V equals P times V. The new pressure is going to be 3 times 10 divided by 14. And for the methane, P times V equals P times V. The new pressure of methane would be 2 times 4 divided by 14. So this math gives us a final pressure of hydrogen of 2.1 atmospheres, and the pressure of the methane is 0.57 atmospheres. The rule for adding these together is to use the least number of decimal places. So we get a total pressure of 2.7 atmospheres. Now I'm going to show you a different way to solve this problem using the ideal gas law. So we were lucky in that we were actually given the temperature and the volume and the pressure, so we can calculate the number of moles. If we had not been given the temperature, we would have had to use Boyle's law, as I already showed you. But let's assume that we can go ahead and calculate the number of moles of hydrogen using N equals PV over RT. So 3 times 10, pressure times volume, divided by the gas constant that contains atmospheres, and then the temperature in Kelvin. If we do this math for the hydrogen and for the methane, we get 1.2 moles of hydrogen, and we get 0.33 moles of methane. Now the total pressure would be based on the total number of moles, which would be 1.5 moles. And that would be nRT over V, where the final volume is the entire container, 14 liters. And if we do this math, we get a number that's pretty close to the value we calculated earlier. It was 2.7, this is 2.6. All right, let's take a look at our next example problem, which has to do with the partial pressure, relating it to the mole fraction. So calculate the mole fraction of each gas in the mixture. Interesting that you don't necessarily need to know the moles of each gas. You could also do mole fraction based on pressure ratios. So in our Boyle's law calculation that we did earlier, the total pressure was 2.7 atmospheres, and we simply use the partial pressure of each gas divided by the total pressure. If we knew the number of moles from the ideal gas law, we would do moles of each gas divided by total moles. And you can see we get pretty similar results. So approximately a mole fraction of 0.8 for hydrogen and about 0.2 for the methane. So in this next problem, we are given some information about how a gas was collected by water displacement. So what does that mean, water displacement? It means that there was a bottle or a tube that was used to collect a gas. It was initially filled with water, and as the gas goes into the tube, it pushes the water out. Now it says here that once the experiment was complete, the height of the collection tube was adjusted so that the water levels inside and outside the tube were the same. Explain why this was done. On page 401, figure 10.15, you can see that they were collecting some oxygen gas from a chemical reaction. The oxygen was bubbled through the water into a collection bottle, and the bottle was raised or lowered until the water level in the bottle equals the water level in the dish. At this point, the total pressure inside the bottle is equal to the pressure of the atmosphere. And that's why we do it. We know the pressure outside the bottle. We have to figure out how to get the pressure inside the bottle. So by adjusting it until the levels of water are equal on both sides, then you can make that assumption so that the pressure inside the collection tube would be equal to the atmospheric pressure outside. Now we're going to turn to page 1058 in the back of your textbook, and we discover that at 22 degrees Celsius, the vapor pressure of water is equal to 19.83 torr. So in terms of knowing the pressure, the vapor pressure of water, and the total pressure was 755.0 torr, we can use the following equation that appears on page 402 to calculate the partial pressure of the butane gas. The total pressure of the atmosphere and of the collected butane was 755.0 torr. Since we're going to take a look at the pressure of the water from that table in the back of the book as 19.83 torr, that must mean that the pressure of the butane without the water would be 755 minus 19.83. So the pressure of the butane gas without the water is 735.2. And I'm rounding off to 1 decimal place because that's the least number of decimal places. The volume of butane gas collected was 100.0 milliliters. So we have volume, we have pressure, we have temperature because it's assuming it's the same as the water bath, so we don't have the number of moles. Let's go ahead and calculate with N equals PV over RT There's the pressure of the dry butane gas without the water. There's the volume collected in liters. We have the gas constant, which has torr, and we have the Kelvin temperature. So we get 0.0040. I'm using 2 sig figs for my number of moles. And that's based on the temperature, which was the least number of sig figs. Well, remember that we have already recorded the mass of the butane lighter both before and after the experiment. So that difference in mass is 0.21 grams. Molar mass is grams divided by moles. So the molar mass, as calculated from the data in this experiment, is 53 grams per mole. Again, 2 sig figs. Since butane has a molar mass of 58.12 grams per mole, the percent error, which is based on the difference between the two measurements divided by the accepted value, times 100, the percent error is around 9%. Okay, this begins section 10.7, the kinetic-molecular theory of gases. These 5 statements of the KMT are found on page 403. The first one talks about how gases consist of molecules, or you could say particle, that are in continuous random motion. The second statement talks about how the volume of the particles themselves is very small, so negligible, relative to the total volume in which the gas is contained. There are no attractive or repulsive forces between the particles. We have elastic collisions between the particles, which means they don't lose any energy overall, that the average energy does not change with time, and that energy is going to be proportional to the temperature. So these statements are summaries of that information. Part B is asking us to decide if each statement is true or false. There is a blue curve at 0 degrees Celsius, which represents the average distribution of the various speeds of the molecules. And then we have a red curve at 100 degrees Celsius, which has shifted slightly to the right. So, true or false? At a given temperature, each molecule in a gas sample is moving at the same speed. That's false. There is a distribution of speeds. Some molecules are faster, some are slower. But the top of the peak there, that represents the average speed. So right now, with the blue line, the average speed is just under 500 meters per second. At 100 degrees Celsius, the average speed is near 500 meters per second. So we've shifted the average speed to a higher value by raising the temperature. All right, true or false? As the temperature of a gas sample is increased, the average speed increases. Yes, that's definitely true. The distribution curve tends to broaden as the temperature is increased, indicating that the range of molecular speeds sort of spreads out at a higher temperature. And yes, that is also true. So at higher temperatures, there is a wider range or distribution of these values. Part C. This information about the kinetic energy equal to 1/2 mv squared helps us to compare the average speeds of different gases. We've already talked about this earlier, that lighter particles travel at faster average speeds than heavier particles. So for us to arrange these 3 gases in order of increasing average speed, we should start with the heaviest and end with the lightest. So carbon dioxide is the heaviest and neon is the lightest. So we put them in that order from slowest to fastest. Part D, what does the diagram tell us about the relationship between molecular speed and molar mass? Well, you can see that hydrogen has the fastest speed in this diagram, and oxygen has the slowest. Oxygen happens to be the heaviest gas in this list, and hydrogen is the lightest. So for gases, there is an inverse relationship between molar mass and average molecular speed. Lighter is faster, heavier is slower. Section 10.8 talks about molecular effusion and diffusion. Effusion just has to do with a gas escaping from a container. Diffusion has to do with gases mixing with other gases. Either way, it's talking about the rate of speed. Now, as it mentions here, even though a quantitative calculation involving Graham's law is not likely to appear on the AP chemistry exam, it is still a good idea for you to be able to use this equation. So the equation for Graham's law says that the rate of effusion of one gas compared to the rate of effusion for another gas would equal the square root of the molar masses, but we have to flip it. So it's the molar mass of gas 2 divided by the molar mass of gas 1. All right, so here's an example. A certain unknown gas has a rate of effusion that is twice as fast as that of methane, CH4. So the mystery gas X should be lighter than methane, and the rate of effusion would equal the square root of the molar mass of methane divided by the molar mass of the mystery gas. That ratio is 2 to 1 because we said that the mystery gas is twice as fast. 16.042 is the molar mass of methane, and we don't know the molar mass of X. Let's square both sides, solve for X, and it turns out that X is equal to 4 grams per mole, which means it is likely that the mystery gas is helium. It weighs 1/4 as much as methane and happens to be traveling twice as fast. All right, section 10.9, we're looking at deviations from ideal behavior. So when does a gas not obey the ideal gas law? Well, gases tend to experience the largest deviations from ideal behavior under conditions of high pressures and low temperatures. So why is that? When you force molecules to be closer together and when you cool them down, they start to experience attractive forces. So the particles of an ideal gas are assumed to occupy no space, so the volume is 0 of the particles themselves, and they would have no attractive forces. However, the particles of a real gas do have finite volumes, and they do experience some attractive forces. Explain why under conditions of high pressure, the volume of a gas tends to be slightly greater than the value predicted by the ideal gas law equation. On page 410, there is a figure, 10.24, that shows that gases behave more ideally at low pressure than high pressure. So on the right, with high pressure, the combined volume of the molecules, which could be neglected at low pressure, cannot be neglected at high pressure. And here from the same page, it says here that at high pressures, the combined volume of the gas molecules is no longer negligible relative to the container volume. So this unoccupied volume, the empty space, is less than the container volume. And at high pressures, gas volumes tend to be slightly greater than those predicted by the ideal gas law equation. So we can no longer ignore the volume of the particles themselves when they are all squeezed together at high pressure. Now explain why under conditions of low temperature, the pressure of a gas tends to be slightly smaller than the value predicted by the ideal gas law equation. Well, what's going on here is that when particles are moving rapidly and randomly in all directions, they experience no attractive forces. But when you slow them down at low temperature, then the attractive forces are going to cause the molecules to stick a little bit to each other, and they're not going to collide with the container walls as much. So temperature determines how effective attractive forces between gas molecules are. As the gas cools, the average kinetic energy of the molecules decreases, and then the molecules are going to begin to experience some level of intermolecular attractive forces, and they would stick to each other rather than bounce off each other. All right, in general, gases tend to experience larger deviations from ideal behavior, we said at low temperatures and high pressures, but also in general as the strength of their intermolecular attractive forces increases. So which chemical, hydrogen or water, would be more likely to deviate from ideal behavior? Well, the answer is water, because of the two molecules, water is going to have stronger attractive forces. We know that water is polar, hydrogen is nonpolar. Water would experience intermolecular forces known as hydrogen bonds. Hydrogen only experiences weak London dispersion forces, and since hydrogen bonding is a stronger type of intermolecular force than London dispersion forces, it's the water molecules that are going to be sticking to each other more likely than the hydrogen molecules. Okay, well, that represents the end of the Chapter 10 packet. I hope that those answers and explanations were helpful. Thanks for watching.